In this video, the product autonomous car will be analyzed and discussed from system engineering point of view, which include 3 stages. And for final report, I will mainly focus on concept development stage. Here are 6 parts related to the product. Background, concept development stage, engineering development stage, post-development stage, system engineering challenges, summary, and lesson learned. Autonomous car is an intelligent system built with computer as the center, which gives the vehicle the ability to get road, pedestrian, and indicator information to perceive environment, plan driving, and automatically control the speed and direction according to the obtained information. From other words, self-driving car is a simple-wheeled robot, which can simulate human driving through the dynamic analysis of surrounding obstacles and analyze of road conditions. All the controls and instructions are given by this computer. Driverless cars use their own hardware to sense the road condition and then control the vehicle to react after calculation. The ultimate goal of driverless car is to realize real driverless driving. Currently, autonomous car can be divided into 2 types. The first is vehicle itself with onboard laser reader, inertial gyroscope, radar, and other sensors to sense the vehicle's road condition and surroundings, which is processed by computer and executed by driving system. Second is the car is related to the Internet of Vehicles, which belongs to the category of intelligent transportation. Autonomous car integrates the science and technology in various fields such as automatic driving, intelligent computing, and artificial intelligence. It reflects the scientific and technological development and technical level of the country and has a broad development prospect in the field of national defense and military and national economy. With the rapid development of the Internet and artificial intelligence like big data and cloud computing, the performance of autonomous car will be further improved. Compared with traditional car, self-driving car has the following new features: real-time navigation, global positioning system, high-speed planning and control, traffic sign visual perception, and dynamic obstacle avoidance. The detailed specification of highly automated driving system and the predecessor system, assistance driving system, will be discussed through system life cycle in following sections. The predecessor system, assistance driving system, featured with single function auxiliary such as anti-lock, constant speed, tactic, but human resource is needed. Currently, advanced assistant driving system is popular and has been used in social life. Compared with the AI system, ADI system adds functions such as adaptive cruise, emergency braking, and path deviation warning. The highly automated driving system has changed a lot from previous 2 stages. Cars equipped with HAD system will be able to drive themselves under specific conditions such as special parts on highway. By analyzing the performance of predecessor system and competing product, we can identify some deficiencies and opportunities. According to the analysis above, the successor system, the highly automatic driving system, would be designed to provide perfect navigation, accurate positioning, good sense of surroundings, traffic sign recognition, and dynamic obstacle avoidance. For navigation approaches, there are 2 ways which is widely used now. First is differential GPS positioning system. Through satellites to locate the car at different locations and send data information back to the base station on the ground and track the car's location for correction. It can avoid noise interference and errors, and the result can reach centimeter level. However, high-rise buildings, tunnels, and any other things can block GPS signals, and the car will easily deviate from the right direction. So other sensing systems are needed to assist. The second is inertial sensors. They can detect and measure acceleration, tilt, impact, vibration, rotation, and multi-degree of freedom motion. After calculating and integrating inertial sensor data, the vehicle information can be obtained in real time, but the inertial sensor itself has the problem of deviation and noise. For machine vision system, engineers equip the vehicle by long-distance cameras on both sides of the front and a short-range radar on the four corners of the car, which assist the vehicle take a close look at the car's surroundings. Short-range radar can quickly detect the moving things around the vehicle and avoid a traffic accident. Camera in the front windshield is for identifying traffic signs, and camera in the rear windshield captures street scenes and determines the precise positioning of the vehicle by comparing and distinguishing with the terrain in the navigation. Operational validation criteria for positioning system that GPS-based positioning methods should be able to reduce external signal interference and able to deal with all kinds of emergencies to achieve more accurate results. And for traffic identification system, the traffic signal information should be accurately obtained by the camera with high resolution in real time, and the control center should rapidly detect the feedback to make the right decision. At the beginning of concept exploration, operational objects are restated. It is that we need perfect navigation systems to ensure cars drive to the right direction. Cloud computing, big data, and other technologies are used to monitor climate data and road conditions in real time, so that the car should make the most time-saving, convenient, and safe road planning during driving. Accurate positioning system to park exactly where drivers want. Most GPS sensors are greatly affected by the environment, and to some extent, inertial positioning can reduce environmental impact, and integrate GPS and inertial sensor data can greatly reduce the error. Traffic condition observation with the assistance with camera and short-range radar around the car in complicated road conditions. The radar should quickly detect the moving things around the vehicle and avoid traffic accident and determine the precise location of the vehicle. Traffic sign recognition captured by the camera will meeting different types of traffic sign, which means it should be able to identify both graphic signal and arrowhead signal when taking photos with the camera and output a precise result. Dynamic obstacle avoidance with LiDAR will meet both stationary and moving obstacles. It is the key to the obstacles of path tracking. We do not only need to realize static road environment problem, but real-time tracking the path of the obstacles. At present, the accuracy of GPS system can reach less than 5 meters. In the practical application process, the sensor combination technology based on common feature mostly used to integrate GPS and inertial sensor data to achieve better positioning accuracy. In addition, some companies also use laser point cloud and high precision map matching, visual distance calculation to correct each other. Also, ultrasonic sensor convert ultrasonic signals into other energy signals with high frequency, short wavelengths, small diffraction phenomenon detected. The strong penetration of liquid and solid can help vehicles detect the external environment and make appropriate response. Ultrasonic sensors are used in vehicle brake assist system and reversing radar to detect obstacles and avoid collision and friction. So the best way is to combine all the positioning methods to position vehicles. The dynamic obstacle avoidance system. Currently, most obstacle avoidance sensors are laser radar, microwave radar, vision, and ultrasonic sensors. Laser sensing and microwave sensing technology uses radar to transmit laser and microwave to around target objects, then receive signal reflected from objects. Vision sensing system is based on image sensor. According to different intensity of current intensity, current signal in the image sensor driving voltage analog signals to complete the digital image. Zigbee and RFID technologies have realized optical information sharing. To the analysis about the concept exploration stage, for performance requirements validation, we can conclude that multi-sensor combination of camera, millimeter wave reader, and ultrasonic reader suitable for automatic logics guidance in airport, factory, and workshops. The combination of laser reader, microwave reader, vision, and ultrasonic sensors will assist build up a round dynamic obstacle avoidance system. Inertial positioning is suitable for local shot time positioning or auxiliary positioning. And GPS positioning is suitable for relatively safe and stable environment. From what we have discussed above, we can find that for differential GPS positioning system, GPS positioning is greatly affected by the environment, and the inertial sensor itself has a problem of large deviation and noise. So the integration of GPS and inertial sensor data based on common feature will have high positioning accuracy, avoided noise interference and error in positioning, and fast-moving vehicle positioning can be accurately calculated. For a better driving experience, single use of sensors and cameras will lead to the amount of data error and help us later will increase funding, which is not easy to put autonomous into the market. So at the present, automatic driving environmental perception mainly include two domains, visual domains and lidar domains. One is multi-sensor combination of camera, millimeter wave reader, and ultrasonic reader represented by Tesla, and the second is multi-sensor combination of low-cost lidar, millimeter wave reader, and ultrasonic sensor and camera represented by Google. So we will find the major changes over the predecessor system are navigation method and positioning method, and the regular changes for our generation is 3D camera, millimeter wave reader, and ultrasonic sensor. Here's a diagram show that those components with bold and underline evolve major changes over the predecessor system, and the other components either retain the same feature of predecessor system or have small changes. In this stage, the design of the whole system will be discussed according to subsystems. Based on the analysis in concept exploration stage, the major updated parts and newly designed functions is included. As mentioned in concept selection phase, positioning system is selected and lidar is the components in hardware system to collect point cloud data in real time, perform object recognition and tracking tasks during driving for obtaining high precision map. Lidar is a collection of laser. It is composed of laser transmitter, optical receiver, turntable, and information processing system. It integrates global positioning system and inertial navigation system for obtaining cloud data to build 3D models and generating accurate digital elevation model. When the car encounters an obstacle, lidar sends a laser beam to the target. The laser turns the electric pulse into an optical pulse and emits it. The optical receiver then converts reflected light pulse back into the electrical pulse and sent into the display. Google, Uber, and other mainstream autonomous car research and development team are using lidar as one of the sensors, which can be used with image recognition and other technologies to assist cars to determine road conditions. Today's camera system adopts complementary metal oxide semiconductor transistor, which can reach 100 to 200 million pixels. A combination of monocular and binocular camera and lidar system can provide a driver with information about the speed, distance, and the shape of obstacle or moving object. Cameras can help drivers detect lane lines, obstacles, and classify roadblocks, and identify traffic signs such as traffic lights and speed limit signs. The light is focused on the sensor after passing through the optical lens and filter. The optical signal is converted to electrical signal through CMOS or CCD integrated circuit, and then converted into standard digital image signal through the image processor, and then transmitted to the computer through the data transmitter interface. Both cameras and lidar cameras can be used for lane detection. In addition, lidar can also be used for curve detection, for license plate recognition and recognition of both sides of the road, such as speed limit plates and traffic lights. Car driving mainly use cameras to complete. If obstacles are identified, the camera can easily classify obstacles through deep learning. Positioning system mainly consists of navigation and positioning satellite position receiver, such as GPS receiver and inertial measurement unit, base station, etc. The GNSS board card receives signal from all visible GPS satellites and real-time kinematics via antenna, and then interprets and calculates its own spatial position. GPS provides more accurate location information with low update frequency, while IMU provides relatively low accuracy location information with high update frequency. Common filter is used to integrate the advantages of two types of data to provide accurate and real-time location updates. IMU updates every 5 milliseconds, but the errors accumulate and the accuracy decreases. However, every 100 milliseconds we can get an update of GPS data to help to correct the errors accumulated by the IMU. As a result, drivers can eventually get real-time and accurate location information. When the vehicle driving through a tunnel or between the tower buildings, streets, since the signal blend area sheltered by tall buildings cannot implement navigation, which requires fusion INS information. INS is independent and disturbed and can provide the whole navigation parameters like position, velocity, and altitude in all weather conditions. Millimeter wave radar is mainly used to detect traffic vehicles and pedestrians. It has the characteristics of fast and accurate detection speed and strong penetrating ability. It has the characteristics for all weather and all day. Millimeter wave radar consists of chip, antenna, and algorithm. The radar emits a beam of electromagnetic wave and calculates the distance and speed by observing the difference between echo and incident wave. The measurement indexes of image accuracy are range detection accuracy, angular resolution, and velocity difference resolution. The higher the frequency of millimeter wave, the wider the bands and the more detailed the imaging. There are two main types, 77 GHz and 24 GHz. Ultrasonic sensor consists of ultrasonic emitter, ultrasonic, and other components of receiver, timer, temperature sensor. Sensor using the ultrasonic velocity in air measure the time of sound wave reflected after launch to meet obstacles, according to the transmitting and receiving time to calculate the launch location to the actual distance from obstacles. Generally, vehicle's ultrasonic radar is usually mounted on the car's bumper. It is mainly used for close range and low obstacle detection to avoid the blind area of close range perception around vehicles. Ultrasonic wave can be directional emission, good direction, easy to control the intensity, do not need to contact with measured object directly. However, it is easily affected by the room temperature and the measure precision is low. Although the current range of ultrasonic ranging can reach 100 meters, but the accuracy of measurement can only reach centimeters, so the accuracy still needs to be improved. In software subsystem, HMI is a significant upgrade and change. HMI is an interactive medium between driver and cars, which to some extent directly affect user experience. Particularly for intelligent cars, it is the most important minded to support users to driving vehicles and enjoy the provided service, which plays a key role in the realization of unmanned driving functions. HMI of traditional cars is also called driver interface. The primary task of a driver is driving, so supporting and assisting driving naturally become a core function of HMI. In addition, secondary tasks such as infotainment and cockpit control are also designed for driving scenes, and the impact on driving safety must be strictly assessed. The core of the traditional HMI design of the automobile can be boiled down to cognitive psychological concept, attention. This concept can be divided to two parts. One is stimulus-oriented attention, and another is called goal-oriented attention. One aspect of HMI design is to avoid driver distractions such as lane driving aids and fatigue warning. On the other hand, to attract the attention of the driver such as car alarm, travel reminder, goal-oriented attention includes all operations and acquisition of purposeful information. It will divert the driver attention from driving to targeted behavior, leading to distracted driving. But when it's done in a way that is very cognitively consistent with a certain level of privacy, it creates an automatic behavior or muscle memory with very low attentional resources that greatly reduces distraction. The core for autonomous car is the shift from attention to trust, which is the most significant change that driverless cars have brought to HMI, and adapting to this change is the key to improve the driverless user experience. The data platform stores all kinds of data from the unmanned vehicle in real time, including perception, vehicle status, driving track, software module status, keylog files detected, and make offline statics analysis, positioning problems, and a training model for the clock platform. Driverless data could come from simulated scenarios or road tests. There are two different sources of simulated scene data, the recorded scene and the virtual scene. The recorded scene can be used to replay the sensor data already observed in the actual road test of the car, and the visual editor can be used to create a new driving scene with the help of virtual scenes, which helps drivers quickly verify and validate the algorithm. To train machine learning models like deep learning network, annotate data with tag needed, which includes traffic light data, observed data with bounding box, and semantic segmentation data. This stage mainly analyzes the production, installation, operation, and support of the system. The special feature of the autonomous car complex system is that it's not only an industry product with complex hardware and physical structures, but also an intelligent robot that requires corresponding algorithms. On the production side, Google uses high precision lidar, GPS, camera, and other scenarios and other sensors to collect road information. At present, Google unmanned vehicles have been able to identify special cleaning by traffic police and make correct judgments in some special circumstances. The focus of research on driverless car lies in the implementation of algorithms, and driverless car require extremely high accuracy of maps, so the data analysis ability need to be further improved. In order to further improve the safety of unmanned driving, the communication between vehicles and the infrastructure must be realized. Also, the information shared between vehicles should be realized. Finally, the ultimate goal of V2E should be realized. In order to realize V2I and V2V, it is necessary to enhance the information sharing ability between platforms. The ultimate goal of the Internet of Vehicles is to achieve V2E, turning vehicles into mobile processing platforms like mobile phones, entertainment, and work platforms for users. The second part is the operation and support of data analysis system. Deep learning has made tremendous progress in image recognition and realized real-time image processing with GPU, efficient image processing performance. High-precision sensor can detect environmental information in complex traffic conditions. At present, sensors can not overcome the signal interference of vehicle movement, environmental climate, and working range, so they cannot ensure the accurate detection of all driving environments. The high price of laser radar sensor also limits the practical application of this technology. In the future, data will be smaller, lighter, more integrated, cheaper, and solid state. In addition, in order to realize automatic driving, it is necessary to combine the integrated control system, the new bus distribution, and automatic driving architecture. The safety of autonomous driving technology can be improved by means of various onboard software of perception and decision algorithms. High precision map and GPS positioning could make autonomous driving easier by reducing the need for sensors in vehicles. Also, the integration of high-performance onboard computing platform with deep learning technology can improve the level of vehicle autonomous driving. Embedded vehicle technology needs high-performance computing platform, integrates onboard computing platform with deep learning technology to enhance their intelligence level. Although companies have made great progress in the field of artificial intelligence and put into the research of autonomous car, there, there's still there's still some big challenges for further development, like sensor combination. Driverless car installed with HD camera and ultrasonic sensor were extremely easy to be disturbed due to some strong light noise and acoustic absorption material. This limits help the obtain of clear and complete image and make it hard to accurately measure the actual distance of obstacles. In addition, the accuracy of these devices decreases dramatically in extreme weather conditions such as high wind, fog, rainstorm, etc. The perception effect of radar and camera is easily affected, and the recognition of traffic lights will be affected correspondingly because the color saturation is different from that in sunny days. Also, achieve efficient and rapid integration of information collected by all kinds of equipment to form a stable and intelligent system is also a big problem to be solved. So, information integration should be realized through multi-sensor cooperation, which is beneficial to assist automobile decision making. The advantages of various sensors needs to be comprehensively utilized to achieve the ideal effect. Hardware and software of self-driving car require huge investment research and development funds for self-driving technology research. Since later is too expensive for mass production, the sensors in the autonomous driving system are mainly millimeter wave sensor and camera. For example, the most expensive device in Google's driverless car is the laser rangefinder, which costs about 70,000 each, or more than half the cost of Google's driverless cars. The high cost is now conducive to the widespread adoption of driverless car in common life. Also, the safety. Driverless cars are connected to the internet, which expose the car to network security problems and increase the cost of building reliable firewalls. If a driverless car is infiltrated through the internet by cyber hackers, it can be controlled remotely, which may deliberately cause a safety accident. By going through all three stages required for system engineering point of view, autonomous car is analyzed and discussions mainly focus on concept development stage. The new system, HAD system, is both technology-driven and need-driven system. Early vehicles have less precise map analysis and road environment identification. Driving systems still relies more on manual driving. Under such circumstances, the HAD system collects sensitive sensor reader, massive data information, and accurate algorithm. With the help of artificial intelligence, autonomous car becomes more and more intelligent and improve the interaction between human and vehicles. By this course, a new product which is regarded as a system in report. The production is discussed not just from the final machine but also from how the new features and functions generate. In whole stage, every practical factors affect the analysis during the whole process. There are trade-offs should be made, such as the accuracy of inertial positioning is high and doesn't affect by external signals, but the error gets bigger over time. Satellite positioning have more satellites but easily affected by weather conditions. Lidar has good sense of surrounding environment, but the price is high and require large development cost. Ultrasonic sensor information transmit speed is also easily affected by extreme weather conditions, but the technology is relatively mature and cheap for short range ranging. For viewing all those factors and resources available, every decision will define the final product. So close and effective collaboration among system engineers, scientists, technologists, and any other related people can ensure the quality of a complex system. So that's all. Thank you very much.